The world has not yet awakened. Across the vastness of interior Alaska, darkness holds the land in perfect stillness. No sound rises from the frozen valleys. No wind disturbs the snow. Above the horizon, stars fade one by one, dissolving into the pale edge of morning. And there, rising from the earth like a monument to time itself, stands Denali, 20,310 feet of ice, granite, and silence, the Great One, as it has been called for thousands of years, the tallest mountain in North America. A frozen giant whose shadow stretches for miles across tundra, forest, and glacier. But this is not a documentary about the summit. This is a story about what lies beneath. Beneath the glaciers, beneath the permafrost, beneath the snowfields that have not melted in millennia, there exists another world. A world of ice caves and subterranean rivers, of frozen tunnels carved by meltwater, of geological mysteries that remain unmapped and unexplored. A world where ancient bones rest in eternal cold, where indigenous knowledge speaks of hidden valleys, and where modern science still searches for answers. If you enjoy calm explorations of history, geology, and the quiet mysteries of the natural world, consider subscribing and sharing this journey with others who find peace in the past. Now, let us step into the silence together. The temperature hovers near 40 degrees below zero. The air is so cold it burns. Every breath becomes visible, crystallizing instantly into a small cloud of ice. The snow beneath your boots does not crunch, it squeaks. That strange, high-pitched sound that only happens when frozen water is compressed at extreme temperatures. You stand at the edge of the Ruth Glacier, one of the great rivers of ice that flow down from Denali's southern face. Before you, the ice stretches into the distance, a highway of white and blue that winds between vertical granite walls. The Great Gorge, they call it. A canyon of ice nearly a mile deep. Above, the sky begins to shift. Not yet sunrise, just the first whisper of light. A pale glow behind the peaks to the east, turning the blackness into deep blue, then violet, then the softest shade of rose. Denali emerges slowly from the darkness. First, the summit, a pyramid of white catching the light while everything below remains in shadow. Then the ridges, the glaciers, the hanging ice fields that cling to slopes so steep it seems impossible they do not fall. The mountain reveals itself in layers. And as the light spreads, you begin to notice something else. Silence, not the absence of sound, but the presence of it. A silence so complete it becomes almost tangible, something you can feel against your skin. In this silence, you can hear the mountain breathing. The faint creak of ice shifting deep within a glacier. The distant rumble of an avalanche miles away, muffled by distance and cold. The whisper of wind-driven snow sliding across a frozen surface. This is the sound of deep time. The sound of a landscape shaped not by years or decades, but by millions of years. A place where the past is not buried and forgotten, but preserved, frozen, waiting. And it leads us to the question that shapes this documentary. What lies hidden beneath Alaska's frozen wilderness? Beneath the glaciers that cover thousands of square miles. Beneath the permafrost that extends hundreds of feet into the earth. Beneath the snow that falls and compresses and transforms into ice over centuries. Are there caves we have never mapped, rivers that flow in darkness beneath the ice? valleys that have been sealed away for thousands of years. And what might those frozen places preserve? The remains of ancient animals, mammoths and lions and camels that walked across Beringia when the world was younger. Evidence of the first people who traveled through these lands, following caribou and memory across a landscape of ice. Geological records that could tell us how the climate has shifted, how mountains rise and fall, how ice ages come and go, or perhaps something more. Stories passed down through generations. Tales of hidden shelters beneath the ice. Legends of beings who lived in the frozen darkness. Modern rumors that blend indigenous tradition with internet speculation, creating mysteries that are difficult to untangle. We will explore all of it. But we will do so carefully, with respect for both science and story, distinguishing always between what we know, what we wonder, and what we imagine. The sun touches the summit. For just a moment, the peak of Denali burns gold. Then the light descends, pouring down the mountain's faces, illuminating ridge after ridge, glacier after glacier, until the entire massif stands revealed against the morning sky. 20,000 feet of stone and ice. And beneath it all, a world we are only beginning to understand. To understand what lies beneath the ice, we must first understand how the ice came to be. And to understand that, we must go back, far back. 56 million years ago, the land that would become Alaska did not exist as we know it today. The Pacific Plate, a vast slab of oceanic crust, moved steadily northward, grinding against the western edge of the North American continent. The collision was slow, relentless, inevitable. And from that collision, mountains began to rise. This is the mechanism of plate tectonics. The engine that builds mountain ranges, reshapes continents, and drives the slow dance of geology across deep time. As the Pacific Plate subducted beneath North America, diving down into the mantle, its movement forced the overlying crust upward. The Alaska Range was born, not all at once. Not in a single catastrophic event, but slowly, over millions of years, inch by inch, foot by foot, the land rose. Sedimentary rocks that had formed at the bottom of ancient seas were folded, fractured, and thrust skyward. Granite plutons, massive bodies of molten rock, pushed up from below, cooling slowly into the crystalline stone that now forms Denali's core. The mountain grew. By 6 million years ago, the Alaska Range had achieved significant height. But Denali itself, the towering giant we know today, was still rising faster than the surrounding peaks. Its position at the intersection of major fault lines gave it a geological advantage. The Denali Fault, a massive strike-slip fault similar to California's San Andreas, runs directly along the range's southern flank. The mountain sits at a point of tremendous tectonic stress, and it is still rising. Modern GPS measurements show that Denali continues to gain height at a rate of approximately 1 millimeter per year. A tiny increment, barely perceptible in a human lifetime. But across geological time, these millimeters accumulate into miles. The mountain is not finished growing, but uplift alone does not explain the landscape we see today. To understand the glaciers, the ice caves, the frozen rivers beneath the surface, we must understand what happened next. The Ice Ages. Beginning roughly 2.5 million years ago, Earth's climate began to oscillate between warm periods and cold. The causes are complex, involving subtle variations in the planet's orbit, changes in ocean circulation, fluctuations in atmospheric carbon dioxide. But the result was dramatic. During cold periods, ice accumulated. Snow fell on the high peaks and did not melt. Year after year, century after century, it piled up. Under its own weight, the snow compressed, transforming into dense glacial ice. And when the ice grew thick enough, it began to flow. Glaciers descended from the mountains. Massive rivers of ice, thousands of feet thick, carving through valleys with the slow, irresistible force of frozen water. They scraped away soil, ground down bedrock, carried boulders the size of houses, and deposited them miles away. They reshaped the entire landscape. At the peak of the last glacial maximum, roughly 20,000 years ago, ice covered much of Alaska. The Alaska Range was buried beneath glaciers far larger than those we see today. Only the highest peaks emerged from the ice, isolated pyramids rising from a frozen sea. Denali stood above it all, but even here, glaciers clung to the mountain's flanks, flowing down every valley, merging into vast ice sheets that extended for hundreds of miles. Beneath that ice, something remarkable was happening. Where the glaciers ground against bedrock, friction generated heat. Meltwater formed, even in the midst of the Ice Age. This water, trapped between ice and stone, began to flow. It carved channels, dissolved rock, created networks of drainage that existed in complete darkness. Subglacial rivers were born. At the same time, in areas where the glaciers did not reach, a different process was underway. Permafrost was forming, ground that freezes and remains frozen year-round, sometimes extending hundreds of feet below the surface. Permafrost is not merely frozen soil. It is a complex matrix of ice, rock, organic material, and time. It preserves everything: seeds, pollen, bones, entire ecosystems locked in cold storage. And within the permafrost, ice can form unusual structures. Massive wedges of pure ice, underground lenses that grow over centuries, even cavities and voids where ice has sublimated away. The frozen underground became a labyrinth. Then, roughly 11,700 years ago, the climate warmed. The last ice age ended. Glaciers retreated, though they did not disappear. Much of the permafrost remained frozen, and the landscape we see today emerged from beneath the ice. But the ice did not simply vanish. It left behind clues, records, structures. Glaciers still flow from Denali's heights, carrying with them the slow memory of ancient snow. Permafrost still grips the land, preserving fragments of the past. And beneath the surface, in places we have only begun to explore, the frozen architecture of the ice ages endures. This is the foundation, the geological stage upon which the rest of our story unfolds. There is water flowing beneath the glaciers of Denali. You cannot see it from the surface. The ice above is hundreds, sometimes thousands of feet thick, but it is there, moving in darkness, carving channels through bedrock, reshaping the hidden landscape with patient, relentless force. These are subglacial rivers. To understand how they form, imagine the base of a glacier. The weight of ice above creates immense pressure. This pressure, combined with friction as the glacier slides over bedrock, generates heat. Even in the depths of winter, when surface temperatures plunge to 40 or 50 below zero, the boundary between ice and stone can be warm enough for water to exist in liquid form. This meltwater has to go somewhere. It follows the path of least resistance, flowing along the bedrock surface, collecting in channels, merging with other streams until entire river systems exist beneath the ice. Some of these rivers flow for miles before emerging at the glacier's terminus in powerful, milky torrents. The water is grey with rock flour, sediment ground so fine by the glacier's movement that it remains suspended in the water, giving glacial rivers their distinctive color. This cloudy water carries with it the evidence of erosion, the slow grinding work of ice on stone. But the rivers do not only flow along bedrock. Sometimes they carve upward into the ice itself. When water flows through a glacier, it melts the surrounding ice, creating tunnels. These meltwater tunnels can be small, just inches across, or vast, large enough to walk through, cathedral-like spaces lit by the blue glow of transmitted light. Entering a glacier tunnel is like stepping into another world. The ice above and around you is not white, but blue. A deep, luminous blue that seems to come from within the ice itself. This color is the result of compression. As snow transforms into glacial ice, air bubbles are squeezed out, and the ice becomes incredibly dense. Dense ice absorbs red wavelengths of light and transmits blue. The effect is otherworldly. Smooth walls curve overhead, sculpted by flowing water into organic shapes. The floor beneath your feet is slick, a mixture of ice and refrozen meltwater. The sound of running water echoes from somewhere deeper in the tunnel, a constant murmur that never stops. The temperature inside is just below freezing, warmer than the outside air, but still cold enough that your breath fogs. Droplets of water fall from the ceiling, the slow drip of a glacier melting from within. In summer, these tunnels can flood with meltwater. In winter, they freeze solid, sealing themselves until the next thaw. These tunnels are not permanent. A glacier is always moving, always changing. Tunnels that exist one year may collapse or close the next. New passages open as water finds new routes through the ice. The entire system is dynamic, ephemeral, a shifting maze of frozen channels. But some structures are more stable. Ice caves form where glaciers encounter bedrock cliffs or where meltwater has carved large chambers that remain relatively protected from the glacier's movement. These caves can persist for years, even decades, their entrances visible as dark openings in the white face of the ice. The Kastner Glacier in the eastern Alaska Range contains ice caves that have become well known to adventurous visitors. The entrance is a gaping mouth at the glacier's terminus, opening into a passage that extends deep into the ice. Inside, the walls are sculpted into smooth, flowing shapes. Light filters through the ice, turning everything blue and green and turquoise. It is silent inside the ice. The outside world disappears. The only sounds are the drip of water, the occasional groan of ice settling, the crunch of your footsteps on the frozen floor. And everywhere, there is the sense of being inside something alive. A glacier is not a static object. It flows, it breathes, it responds to temperature and pressure and the passage of time. Standing inside one, surrounded by ice that may be centuries old, you feel the presence of that slow movement. But not all of Alaska's ice is accessible. Much of it remains unmapped, unexplored. The glaciers that flow from Denali are remote, dangerous, and constantly changing. Many have never been entered. The caves and tunnels within them exist in darkness, known only to the water that flows through them. And then there is the ice beneath the permafrost. In areas where the ground remains frozen year-round, ice can exist in forms that have nothing to do with glaciers. Massive ice wedges form when water seeps into cracks in the soil and freezes, expanding, forcing the crack wider. Over thousands of years, these wedges can grow to enormous size, some extending more than 20 feet deep and several feet wide. Sometimes, the ice creates chambers, voids in the permafrost where ice has sublimated, turning directly from solid to vapor without passing through a liquid phase. These cavities are rare, difficult to detect, and almost never explored. They exist as negative space within the frozen ground, small pockets of absence surrounded by ice and soil. Could there be larger voids, caverns formed by ancient processes we do not fully understand? Networks of spaces beneath the permafrost, accessible only through cracks or collapses in the frozen earth. It is possible. We know that permafrost is not uniform. It varies in thickness, in temperature, in the amount of ice it contains. In some areas, ground ice makes up more than 50% of the volume. When that ice melts, the ground collapses, creating sinkholes, depressions, even small lakes. What happens when the ice does not melt, but instead creates stable voids? Science does not yet have complete answers. The frozen underground remains one of Alaska's great unknowns. We have mapped the surface in extraordinary detail. We have used satellites to measure glacier movement, LiDAR to create elevation models, ground-penetrating radar to peer beneath the ice. But there are limits to what technology can reveal. And in the spaces beyond those limits, in the darkness beneath the glaciers and the frozen silence of the permafrost, there remain mysteries, unmapped chambers, unexplored tunnels, rivers that flow where no human has ever traveled. The ice keeps its secrets, but it also keeps records. And to understand what those records might tell us, we must turn our attention to the people who first walked across this frozen land, long before maps or nations or names. The first Alaskans, who knew the ice not as a mystery to be solved, but as a part of the world to be understood, respected, and remembered. 15,000 years ago, the world was a different place. Sea levels were lower, hundreds of feet below where they stand today. So much water was locked in glaciers and ice sheets that entire continental shelves lay exposed to the air. And between Asia and North America, where the Bering Strait now separates two continents, there stretched a land bridge. Beringia, not a narrow corridor, but a vast subcontinent, 1,000 miles wide from north to south. A cold grassland, a steppe tundra populated by mammoths and horses, bison and caribou, lions and bears. A landscape harsh and beautiful and unimaginably remote. And across this land, people traveled. We call them Paleo-Indians, though that name encompasses many groups, many cultures, many stories that we will never fully know. They were hunters, following the great herds that moved with the seasons. They were survivors, adapting to one of the harshest environments on Earth. They carried with them knowledge, language, tradition, and they walked into Alaska. The archaeological evidence for these first migrations is fragmentary but growing. stone tools found at the Swan Point site along the Shore Creek Flats in central Alaska have been radiocarbon dated to approximately 14,000 years ago. The Broken Mammoth site, not far away, has yielded similar dates. These are among the oldest confirmed human occupations in Alaska. The tools tell us something about the people who made them. Small, carefully crafted blades, microblades, struck from prepared cores, designed to be set into bone or antler handles. This technology shows sophistication, planning, a deep understanding of stone and how to shape it. But stone tools are only one part of the story. The people who came to Alaska brought with them oral traditions, knowledge systems, relationships with the land that cannot be preserved in archaeological sites. And over thousands of years, as populations grew and diversified, distinct cultures emerged. Among these were the Denali peoples. The Denali, also known as Athabascans, are indigenous peoples whose traditional territories span much of interior Alaska and extend into Canada. Their languages belong to the Nardine family, one of the major language groups of North America. Their presence in Alaska extends back thousands of years, though the exact timeline is still debated by scholars. What is clear is that the Denali developed profound knowledge of the land. They understood the movement of caribou herds across hundreds of miles. They knew where fish gathered in summer rivers. They could read weather in the shape of clouds, predict ice conditions on lakes and rivers, navigate through forests and across tundra using landmarks and memory. And they knew the mountains. For the Denali people of the region, the great peak we now call Denali was, and is, a sacred presence. In the Koyukon language, it is Dinil, the tall one. In other Athabascan languages, it carries similar meanings. The Great One, the High One. A mountain that defines the landscape, visible from hundreds of miles away. The mountain was not climbed. This is important to understand. In many indigenous cultures of Alaska, mountains were places of power, of spirits, of forces that demanded respect. They were not challenges to be conquered, but presences to be acknowledged. Climbing to the summit would have been not an achievement, but a transgression. Instead, the relationship with the mountain was one of coexistence. People traveled through the valleys and foothills. They hunted, they fished, they gathered. They observed the mountain through seasons and years. They incorporated it into their stories, their cosmology, their understanding of the world. Some of these stories speak of the land beneath the ice. Here, we must be careful to distinguish between archaeological evidence and oral tradition. Archaeological evidence consists of physical remains that can be dated, measured, analyzed through scientific methods. Oral tradition consists of knowledge passed down through generations, stories that carry cultural meaning, history, and wisdom. Both are valuable, both deserve respect, but they are not the same kind of evidence. In some Athabascan traditions, there are stories of people taking shelter in caves during harsh winters, of finding protected places beneath overhanging ice or in the lee of glaciers, of discovering valleys where the wind did not reach, where snow did not pile as deep. These stories reflect practical knowledge. In a landscape where winter temperatures can drop to 60 below zero, where storms can last for days, knowing where to find shelter could mean the difference between life and death. Caves, whether formed in rock or ice, offer protection from wind. Even a small increase in temperature, a few degrees gained by being out of the wind, can be significant. Did Athabascan peoples use ice caves for shelter? The archaeological record does not currently provide clear evidence of regular ice cave habitation. This is not surprising. Ice caves are ephemeral. They form, persist for a time, then collapse or melt. Any evidence of human use would be destroyed along with the cave itself. But the absence of evidence is not evidence of absence. It is entirely plausible that people occasionally sheltered in ice caves or near glacier margins. It is plausible that they knew of specific caves, passed knowledge of their locations through oral tradition. What we can say with certainty is that indigenous peoples lived in close relationship with ice and snow for thousands of years. They were not strangers to the frozen landscape. They were experts. Travel in winter often meant travel on ice. Rivers froze solid, becoming highways through the forest. Lakes became crossable. The snow itself, which could be impassable in autumn before it compacted, became firm enough to support sleds and snowshoes. The Denali developed technologies for ice and snow travel. Snowshoes allowed movement across deep snow. Sleds, pulled by dogs or by people, carried supplies and game. Clothing made from caribou hide, with the fur turned inward, provided insulation even in extreme cold. Ice chisels, used to create fishing holes in frozen rivers, were crafted from bone or antler. Every aspect of life was adapted to the cold, and through it all the mountain watched. Denali, rising above the tundra, visible from summer hunting camps and winter villages. A constant presence, a marker in the landscape, a part of the world that was always there. When European explorers first arrived in Alaska, they brought with them different ways of seeing the land. They saw resources to be extracted, territory to be claimed, blank spaces on maps to be filled in. They brought names that would replace older names, stories that would overlay older stories. But the Denali remained. They remain today, carrying forward languages, traditions, knowledge that stretches back thousands of years. Their relationship with the land, including the frozen places beneath glaciers and permafrost, is not a mystery to be solved, but a connection to be maintained. As we continue our exploration of what lies beneath Alaska's ice, it is important to remember that this land has never been empty. It has always been known, always been inhabited, always been home. The frozen echoes we seek include human voices. And those voices have been speaking for 15,000 years. The first Europeans to see Alaska were Russian. In 1741, Vitus Bering, a Danish navigator sailing under the Russian flag, led an expedition across the North Pacific. On July 16th, his ship, the St. Peter, sighted land. Mountains rose from the sea, their peaks white with snow. Bering had reached Alaska. The expedition did not go well. Storms battered the ships. Scurvy weakened the crews. Bering himself died on the return voyage, stranded on a remote island that now bears his name. But the expedition had achieved its goal. It had proven that America could be reached from Russia, and it had brought back something valuable: sea otter pelts. The fur trade began almost immediately. Russian merchants and trappers pushed eastward along the Aleutian Islands and into mainland Alaska. They established settlements, built trading posts, and brought Orthodox Christianity to indigenous communities. but the Russian presence in Alaska was concentrated along the coast. The interior, where Denali rises, remained largely unexplored by Europeans. It was too remote, too difficult to reach, and it lacked the sea otters that made coastal Alaska profitable. Maps from this period show the coastline in increasing detail, but the interior is blank, marked only with speculative mountain ranges and imaginary rivers. The Denali peoples continued to live as they had for centuries. This changed slowly, beginning in the mid-1800s. In 1867, the United States purchased Alaska from Russia for $7.2 million. The transaction was controversial. Critics called it Seward's folly after Secretary of State William Seward, who negotiated the deal. What could America possibly want with a frozen wasteland? The answer came 30 years later: gold. In 1896, gold was discovered in the Klondike, across the border in Canada's Yukon Territory. News of the discovery triggered a stampede. Tens of thousands of people rushed north, desperate to reach the goldfields before the best claims were taken. Many came through Alaska. They traveled up the Inside Passage by steamship, then struggled over the Chilkoot Pass or the White Pass, carrying supplies on their backs. Those who survived the passes built boats and floated down the Yukon River to Dawson City. Others searched for gold in Alaska itself. Prospectors spread out across the interior, following rivers, panning gravel bars, staking claims. Some struck it rich, most did not, but their travels began to fill in the blank spaces on the maps. In 1902, a prospector named William Dickey published an account of his travels in interior Alaska. He described seeing an enormous mountain, far higher than any other peak in the region. He estimated its height at 20,000 feet, and he gave it a name, Mount McKinley, after the recently elected president, William McKinley. The name was controversial from the start. Indigenous peoples already had names for the mountain. Denali, the Great One. Dickey's renaming was an act of erasure, replacing thousands of years of indigenous knowledge with a political statement. But the name stuck, at least officially, for more than a century. The mountain's immense height attracted attention. Was it really 20,000 feet tall? Could it be climbed? Expeditions were organized, funded by wealthy patrons, scientific societies, and newspapers eager for stories of adventure. The first serious attempt came in 1903. Judge James Wickersham led a small party toward the mountain from the north. They made it to approximately 8,000 feet before being turned back by cliffs and ice. The route they attempted, now called the Wickersham Wall, would not be successfully climbed for another 60 years. In 1906, Frederick Cook claimed to have reached the summit. He returned with a photograph showing a man standing on a snowy peak holding an American flag. The achievement was celebrated and Cook became famous, but doubts emerged quickly. Other climbers examined the photograph and the route Cook described. The details did not match. The peak in the photograph appeared to be a much smaller mountain, miles from the true summit. Eventually, Cook's claim was thoroughly debunked. He had not climbed Denali. He had climbed a foothill and lied about it. The first confirmed ascent came in 1913. A team led by Hudson Stuck, an Episcopal archdeacon, and Harry Carstens, a seasoned Alaskan guide, successfully reached the summit on June 7th. The climb took months of preparation, weeks of effort, and required extraordinary endurance. The team included Walter Harper, an Athabascan man who was the first person to step onto the true summit. This detail is often overlooked in historical accounts, but it is significant. The first person to stand on top of Denali was Indigenous, a member of the Denali people who had known the mountain for thousands of years. Stuck's account of the expedition describes the brutal cold, the altitude sickness, the crevasses hidden beneath snow bridges, the constant danger of avalanches. He also describes moments of extraordinary beauty: sunlight on ice fields, the view from high camps looking out over hundreds of miles of wilderness, the profound silence of the mountain. The climb did not reveal what lay beneath the ice, but it marked a shift in how outsiders understood the landscape. Denali was no longer just a blank space on a map, a distant peak glimpsed by travelers. It was a known quantity, measured, climbed, documented. In 1917, the area around the mountain was designated Mount McKinley National Park. The creation of the park was driven partly by conservation concerns. Wildlife populations, particularly Dall sheep and caribou, were declining due to market hunting. Charles Sheldon, a naturalist and hunter, campaigned for protection, arguing that the region's wildlife and scenery deserved preservation. The park was small at first, just a few thousand square miles, but it represented a new way of thinking about Alaska's wilderness, not just as a resource to be exploited, but as something valuable in its own right, a place worth protecting. Over the following decades, surveyors and scientists gradually explored the park. They mapped glaciers, studied wildlife, documented plant communities. They measured ice thickness, tracked glacier movement, collected weather data. Slowly, the understanding of Denali's geology and ecology deepened, but much remained unknown. The glaciers were too dangerous to explore thoroughly. The permafrost extended too deep to excavate. The caves and tunnels beneath the ice were inaccessible, unmapped, known only as theoretical possibilities. And alongside the scientific exploration, stories began to circulate. Prospectors and trappers, spending long winters in remote cabins, told tales of strange things seen in the mountains. Valleys that appeared on maps but could not be found on the ground. Warm springs emerging from beneath glaciers. Caves that seemed to go down forever into the ice. Most of these stories were second-hand, impossible to verify. But they added to the sense that Alaska's frozen interior still held secrets, that beneath the surface, beyond the reach of explorers and scientists, there were places that remained hidden. In 1980, Mount McKinley National Park was expanded and renamed Denali National Park and Preserve. The name change restored the mountain's indigenous name to official use, at least at the park level. The federal government would take another 35 years to follow suit, but the shift had begun. The park now protects more than 6 million acres of wilderness. Within its boundaries, glaciers flow, permafrost grips the land, and ice caves form and collapse with the seasons. Research continues, using modern technology to peer beneath the surface, to understand the hidden hydrology, to map the unmapped. But even now, with satellites and ground-penetrating radar and decades of study, large parts of the park's subsurface remain unexplored. The frozen echoes beneath Denali do not give up their secrets easily. There is a glacier on Denali's southeast flank called the Ruth Glacier. It flows for more than 30 miles, from the mountain's high ice fields down through a narrow gorge, finally spreading out onto the lowlands. At its deepest point, the Ruth Glacier is nearly 4,000 feet thick, 4,000 feet of ice. To put that in perspective, it is nearly 3/4 of a mile. If you could stand at the bottom of the ice and look up, you would see nothing but the deep blue of compressed glacial ice, layered over centuries, pressing down with unimaginable weight. But you cannot stand at the bottom. Between the ice and the bedrock below, there is only a thin film of meltwater, flowing in darkness, carving channels we have never seen. What we know about these hidden spaces comes primarily from indirect evidence. Scientists use ice-penetrating radar, sending radio waves down through the glacier and analyzing the reflections that bounce back. Different materials reflect differently. Ice looks one way, water another, bedrock another. By analyzing these reflections, researchers can create a picture of what lies beneath, and what they have found is remarkable. Beneath the Ruth Glacier, there are channels carved into the bedrock, gouged by the slow grinding movement of ice over stone. Some of these channels are hundreds of feet deep, canyon-like features that exist in complete darkness. Water flows through them during summer months. The meltwater is under tremendous pressure from the weight of ice above. It flows uphill, following the hydraulic gradient, carving new routes through the glacier's base. In some places, the water pressure is sufficient to lift the glacier slightly, reducing friction and allowing the ice to move faster. This is called basal sliding. It is one of the mechanisms by which glaciers flow, and it is directly connected to the hidden hydrology beneath the ice. Without the meltwater, without the channels and the pressure and the flow, glaciers would move differently, slower, less dynamically. The water is not just eroding rock, it is shaping the glacier itself, but radar can only tell us so much. To truly understand what lies beneath a glacier, you need to enter it, and in a few rare places, that is possible. In 2012, a team of scientists and cave explorers entered a glacier cave system on the lower reaches of the Matanuska Glacier, about 150 miles south of Denali. The entrance was a moulin, a vertical shaft carved by meltwater, dropping down into the ice. They descended on ropes, headlamps cutting through the darkness. Inside, they found a network of passages extending for hundreds of feet, walls of blue ice sculpted into smooth, organic curves, chambers where the ceiling arched overhead 20 or 30 feet high. Streams of meltwater flowing across ice floors, disappearing into cracks and crevices. And in one chamber, something unexpected. Sediment, layers of silt and gravel embedded in the ice, marking periods when the glacier had advanced over bare ground, incorporating the soil into its mass. Within that sediment were fragments of organic material. Twigs, leaves, seeds. They collected samples and sent them for radiocarbon dating. The organic material was more than 1,000 years old. This is one of the remarkable properties of glacial ice. It preserves things. The cold is so constant, the environment so sealed from air and light and the usual processes of decay, that organic material can remain intact for centuries, even millennia. And if ice caves can preserve plants, what else might they preserve? In the permafrost regions of Alaska, outside the glaciers but still within the frozen ground, discoveries have been even more dramatic. In 2012, a mammoth calf was discovered in the permafrost of Siberia, just across the Bering Strait from Alaska. The calf, named Luba, was so well preserved that her internal organs were intact. Scientists could see what she had eaten before she died, could analyze the bacteria in her gut, could reconstruct the final days of her life more than 40,000 years ago. Alaska has yielded similar discoveries. In 1979, a gold miner near Fairbanks discovered the frozen remains of a steppe bison. The animal had died more than 36,000 years ago, but its hide, muscles, and even some internal organs were still present. Scientists named it Blue Babe, after the bluish mineral staining on its hide. Blue Babe now stands, taxidermied, in the University of Alaska Museum of the North. But it is not the only Ice Age animal to emerge from Alaska's permafrost. Mammoth tusks are found regularly, eroding out of river banks or exposed by mining operations. Bones of ancient horses, lions, camels, all species that vanished from Alaska at the end of the Pleistocene, turn up in thawing ground. Each discovery adds to our understanding of the past. The animals tell us what the climate was like, what plants grew, how ecosystems functioned. DNA extracted from frozen tissue allows scientists to study evolution, migration, population genetics. Even gut contents, when preserved, provide snapshots of ancient landscapes. The permafrost is a frozen archive, and we are only beginning to read it. In recent years, scientists have started using a new technique to explore what lies beneath the ice. It is called ground-penetrating radar, or GPR. The principle is similar to ice-penetrating radar, but it is designed for use on foot, with a person walking across the surface pulling a small sled-mounted radar unit. The radar sends pulses into the ground and measures the reflections. Different layers of soil, ice, and rock produce different signatures. With enough data, researchers can create three-dimensional maps of subsurface structures, buried river channels, ice wedges, potential voids in the permafrost. In 2015, a GPR survey was conducted in a section of Denali National Park. The goal was to map permafrost distribution and understand how climate change might be affecting the frozen ground. The researchers walked transects across tundra, forests, and river valleys, recording data at every step. What they found was a complex subsurface landscape. Permafrost was not uniform. In some areas, it extended more than 200 feet deep. In others, particularly beneath rivers and lakes, it was absent. Ice wedges crisscrossed the frozen ground in polygonal patterns, creating a hidden geometry beneath the surface. And in a few locations, the radar showed anomalies, voids. Empty spaces within the permafrost, surrounded by ice and frozen soil. The voids were not large, most just a few feet across, but they were there, confirmed by the radar, unexplained by standard models of permafrost formation. What were they? The researchers proposed several possibilities. Air pockets formed by uneven freezing, spaces where ice had sublimated away, old animal burrows that had been frozen and preserved, or perhaps small caves formed by groundwater movement before the permafrost locked everything in place. Without excavation, it was impossible to know for certain, and excavation was not practical. Digging into permafrost is difficult, expensive, and potentially dangerous. If the permafrost begins to thaw during excavation, the entire structure can collapse. So the voids remain unexplored, small mysteries in the frozen ground, detected by radar but never seen by human eyes. These are the kinds of hidden spaces that exist beneath Alaska. Not vast underground cities, not ancient technological installations, but real physical structures formed by geological processes. Ice caves that form and collapse with the seasons. Subglacial channels carved by meltwater. Voids in the permafrost created by freezing and thawing cycles. They are not legendary, they are not supernatural, but they are mysterious in the truest sense of the word. Unknown, unexplored, full of potential discoveries, and every year more of them are found. In 2018, a hiker in Denali National Park reported seeing an ice cave near the terminus of the Muldrow Glacier. Rangers investigated and found a large opening in the ice, leading to a chamber roughly 50 feet deep. The cave was unstable, at risk of collapse, so it was marked as a hazard and closed to public access. But photographs were taken before the closure. The images show walls of translucent blue ice, light filtering through from above, a stream of meltwater flowing across the floor. The chamber is beautiful, alien, temporary. Within a few years, it will likely collapse or be crushed by the glaciers' movement. But for a brief moment, it existed. A window into the hidden world beneath the ice. These discoveries continue year after year as glaciers retreat, as permafrost thaws, as the climate shifts. What was once locked away in frozen darkness is being revealed, and with those revelations come questions. What else is hidden beneath the ice? What other caves exist, unmapped and unexplored? What remains of ancient ecosystems, frozen in time, waiting to be found? And perhaps more intriguingly, what stories have been told about these hidden places? What legends have grown up around the ice, the darkness, the frozen unknown? To explore those questions, we must turn our attention from science to story, from the measurable to the mythic, from what we know to what has been imagined. Stories live in the cold, long before written records, before maps and surveys and scientific expeditions. The people of interior Alaska told stories by firelight. Stories that explained the world, that carried knowledge, that connected the present to the deep past. Some of these stories were about the mountain. In Koyukon Athabascan tradition, there are accounts of powerful beings associated with high places. Spirits that dwell in the mountains, that control the weather, that must be approached with respect and caution. These are not gods in the Western sense, but presences, forces within the landscape that have agency and awareness. The mountain is not merely rock and ice, it is alive with meaning. To be clear, we are now discussing oral traditions and folklore. These are not archaeological claims or scientific hypotheses. They are cultural knowledge, stories that carry significance within indigenous communities. They deserve respect as such, but they belong to a different category of understanding than the geological and historical evidence we have discussed previously. That distinction is important. In some accounts, there are references to people seeking shelter from storms in protected places, caves in the rock, overhangs beneath glaciers, valleys where the wind did not reach. These stories reflect practical knowledge about survival in extreme environments. They may also reflect something more. The Athabascan peoples understood that the landscape was not static. Mountains rose and fell over deep time. Rivers changed course. Ice advanced and retreated. What was hidden could be revealed. What was open could be sealed away. There are stories, passed through some families, of warm valleys hidden in the mountains, places where hot springs emerged from the ground, melting the snow even in the depths of winter, where plants grew that could not survive elsewhere, where animals gathered, drawn by the heat and the vegetation. Are such places real? Yes. Geothermal activity exists in Alaska, particularly in regions with volcanic history. Hot springs are well documented. Some occur in remote mountain valleys. Some create localized microclimates where the temperature is noticeably warmer than the surrounding area. So the stories have a basis in observed reality. They describe real phenomena encoded in narrative form, passed down through generations. This is how oral traditions work. They preserve knowledge, but they do so through story, which means the knowledge is often wrapped in metaphor, symbolism, cultural context. Separating the literal from the figurative can be difficult, especially for outsiders. There are also stories of beings that live beneath the ice. Again, we must approach this carefully. In Athabascan cosmology, the world is inhabited by many kinds of beings. Some are human, some are animal. Some are neither, or both, or something else entirely. These beings are part of the fabric of reality, and stories about them serve multiple purposes. They teach moral lessons. They explain natural phenomena. They mark boundaries, both geographical and spiritual. They remind listeners that the world is larger and stranger than it might appear. When stories speak of ice spirits or underground dwellers, they may be describing literal beliefs, or they may be using metaphorical language to express something else, something about the relationship between humans and the frozen landscape. Or both at once. Western science tends to categorize things as either true or false, real or imaginary. Indigenous knowledge systems often work differently, allowing for multiple kinds of truth to coexist. A story can be factually inaccurate and still be true in other ways. It can carry cultural truth, emotional truth, ecological truth. It can preserve knowledge about how to live in a place, how to treat the land, how to understand your role within a larger community of beings. So when we encounter stories about hidden valleys or beings beneath the ice, we should not immediately dismiss them as primitive superstition. Nor should we uncritically accept them as historical documentation. Instead, we should recognize them as a different way of knowing. One elder from the Tanana region, interviewed in the 1970s as part of an oral history project, spoke about the old stories. He said that the ancestors understood things that modern people had forgotten, that they knew the land spoke if you knew how to listen, that the ice remembered. The ice remembered. It is a striking phrase, and in a sense, it is literally true. Ice cores contain atmospheric records going back thousands of years. Glaciers preserve pollen, ash, isotopes that tell us about past climates. Permafrost holds the remains of extinct animals, ancient plants, entire ecosystems frozen in time. The ice does remember, just not in the way the elder meant. or perhaps exactly in the way he meant, just expressed through a different vocabulary. There are also stories from the gold rush era, when prospectors and trappers began spending time in the interior. These men, isolated for months at a time, living in small cabins heated by wood stoves, would tell tales to pass the long winter nights. Some of these tales were about things they claimed to have seen, caves that went deep into glaciers, farther than anyone dared to follow, warm air rising from cracks in the ice, suggesting open spaces below. Sounds in the night, booms and groans echoing across frozen valleys, like something enormous moving beneath the surface. Most of these accounts are second-hand or third-hand, recorded decades later, impossible to verify. They belong to the category of frontier folklore, stories that grow in the telling, shaped by isolation, darkness, and the human need to make sense of an unfamiliar landscape. But some elements appear repeatedly. The caves that go down into the ice, the warm air from below. The sounds of hidden movement. Are these entirely imaginary? Not necessarily. We know that ice caves exist. We know that meltwater can create warm, humid air that rises from glacier cracks. We know that glaciers produce sounds, the creak and groan of ice under stress, the sudden crack of crevasses forming, the rumble of internal collapses. All of these phenomena are real. So the stories, while embellished, may be rooted in genuine observations. Prospectors did encounter ice caves. They did feel warm air rising from glaciers in summer. They did hear strange sounds. They simply did not have the scientific framework to understand what they were experiencing. And in the absence of that framework, they created stories. Stories about vast caverns beneath the mountains. About hidden valleys where it was always warm. About the remnants of ancient peoples who had lived underground, sheltering from the ice ages. These stories circulated in bars and trading posts, in the letters miners sent home, in the diaries of early explorers. And over time, they became part of Alaska's folklore. By the mid-20th century, as aviation opened up Alaska's wilderness to more visitors, the stories began to evolve. Pilots flying over remote regions reported seeing things that did not appear on maps. Valleys that seemed too warm, glaciers with unusual formations, depressions in the ice that suggested hidden voids below. Again, most of these reports were vague, unverifiable, but they fed the growing sense that Alaska still held secrets, that beneath the mapped surface, there were places humans had never reached. And then, in the late 20th and early 21st centuries, something new happened. The internet arrived. Suddenly, every vague report, every half-remembered story, every speculation and rumor could be shared globally, instantly. Forums and websites dedicated to unexplained mysteries began collecting Alaskan stories, and the stories began to change. They merged with other narratives, ancient advanced civilizations, lost technology, government cover-ups, extraterrestrial visitations. The old folklore about ice caves and hidden valleys was reinterpreted through these new frameworks, and one story in particular captured widespread attention. The story of a giant pyramid buried beneath the Alaskan ice. It is important to state clearly, at the outset, there is no credible evidence for a giant pyramid buried beneath the ice in Alaska. None. No archaeological surveys have found it. No geological studies have detected it. No indigenous traditions describe it. It does not appear in any historical records prior to the late 20th century. The story is a modern legend, spread primarily through internet forums, YouTube videos, and conspiracy theory websites, but it is a persistent legend. And understanding why it became popular can tell us something interesting about how stories evolve in the digital age. The earliest version of the pyramid story seems to have emerged in the 1990s. According to the story, a mysterious pyramid, larger than the Great Pyramid of Giza, lies buried beneath the ice somewhere in Alaska. The exact location varies depending on who is telling the story. Some versions place it near Denali. Others put it in the remote Brooks Range or beneath the glaciers of the Alaska Peninsula. The pyramid is described as being constructed from an unknown material, possibly not stone at all, but some kind of advanced composite. It is supposedly far older than any known human civilization, built by a lost race or possibly by extraterrestrials, and it is allegedly being kept secret by the US government. Where did this story come from? Tracing the origins is difficult because the story has been repeated, embellished, and modified so many times, but several elements seem to have contributed to its creation. First, the Alaska Triangle. This is a region roughly defined as the area between Anchorage, Juneau, and Utqiagvik, where a statistically unusual number of people have gone missing over the decades. The actual number is disputed, but figures ranging from 16,000 to 20,000 missing persons are sometimes cited. These disappearances are often attributed to mundane causes. Alaska is vast, wild, and dangerous. People get lost in the wilderness. Small planes crash in remote areas where wreckage is never found. Hunters and hikers misjudge weather conditions and succumb to exposure. The state has challenging terrain, extreme weather, and large areas with no cellular coverage or nearby help. But the term Alaska Triangle suggests something more mysterious. It deliberately invokes the Bermuda Triangle with its implications of paranormal activity. And once that association is made, people begin looking for explanations that go beyond weather and wilderness. Ancient pyramids buried in ice become one such explanation. Second, there is the fact that Alaska does have genuine mysteries. Unmapped caves, unexplored glaciers, vast stretches of wilderness where few humans ever travel. This real unknown creates space for speculation. If much of Alaska is genuinely unexplored, who can say for certain what is or is not hidden beneath the ice? Third, ground-penetrating radar and other remote sensing technologies have become more widely known. Stories began to circulate that military radar installations had detected something large and geometric beneath the Alaskan ice. These stories claim that the discovery was classified, that researchers were sent to investigate, that what they found was so significant it had to be kept secret. No credible sources support these claims. No scientific papers describe such a discovery. No military reports have been declassified mentioning anything of the kind. No researchers have come forward with evidence. The story exists entirely in the realm of rumor and speculation, but it spread widely. YouTube videos with titles like "Giant Pyramid Discovered in Alaska" or What the Government Does Not Want You to Know About Alaska have accumulated millions of views. They typically feature dramatic music, ominous narration, and a mixture of real information, misrepresented science, and outright fabrication. A common technique is to show real images of pyramids from Egypt or Mesoamerica, then transition to images of Alaskan mountains or glaciers, implying a connection that does not exist. Another technique is to cite legitimate scientific work out of context. For example, scientists have used ground-penetrating radar in Alaska to study permafrost and map subsurface ice structures. Videos about the pyramid story will mention this real research, then claim without evidence that the radar detected something artificial, something the scientists are not talking about publicly. This creates a veneer of credibility. Real science is being done in Alaska. Real technologies are being used to look beneath the ice. Therefore, the leap to hidden pyramids seems smaller, more plausible, but the leap is not justified by the evidence. What the radar actually shows are geological features. Ice lenses, frozen soil layers, bedrock topography. These features can sometimes be angular or geometric looking, not because they are artificial, but because of the way ice and rock fracture along natural plains. Geology creates patterns. Frost wedges form polygons. Basalt columns fracture into hexagons. Crystals grow in regular, symmetrical shapes. None of this requires human or extraterrestrial intervention. It is simply how matter behaves under specific conditions. But to someone unfamiliar with geology, a radar image showing angular features might look artificial. And once that seed of doubt is planted, confirmation bias takes over. People start looking for evidence that supports the pyramid theory and ignoring evidence that contradicts it. This is how modern legends are built. There is also a cultural dimension to the pyramid story worth considering. Alaska, in the popular imagination, is America's last frontier. A place of wilderness, isolation, and mystery. It represents the unknown, the untamed, the undiscovered. For people living in densely populated, thoroughly mapped regions, Alaska offers a rare space where imagination can still roam. The idea that something ancient and powerful lies hidden beneath the ice taps into deep human fascinations, lost civilizations, ancient wisdom, secrets waiting to be uncovered. These are archetypal themes appearing in stories across cultures and throughout history. From Atlantis to Shambhala, from the Library of Alexandria to the treasures of the Templars, humans love stories about hidden knowledge. The Alaskan pyramid story is a modern iteration of this ancient narrative pattern, and the internet allows it to spread in ways that were not possible in earlier eras. A story that once would have remained local folklore, told in a single community or region, can now reach a global audience in seconds. It is important to note that most people who share these stories are not deliberately lying. They believe what they are sharing, or at least find it intriguing enough to pass along. The internet creates echo chambers where like-minded people reinforce each other's beliefs. If everyone in your online community accepts the pyramid story as true, it becomes difficult to maintain skepticism. But belief does not create reality. No amount of YouTube videos or forum posts will conjure a pyramid into existence beneath the Alaskan ice. If such a structure existed, it would be detectable through multiple independent methods. It would appear in seismic surveys, in gravity anomaly measurements, in ground-penetrating radar conducted by numerous research teams. It would not remain secret. Science is a collaborative, international enterprise. Thousands of researchers from dozens of countries work in Alaska. The idea that they are all part of a conspiracy to hide evidence of an ancient pyramid is not credible. So why address the story at all? Because it has become part of Alaska's modern folklore. Because it affects how some people perceive the region. And because distinguishing between legend and reality is important if we want to understand what actually lies beneath the ice. The real mysteries of Alaska, the genuine unknowns, are fascinating enough without inventing fictional ones. Unmapped ice caves that form and collapse with the seasons. Subglacial rivers flowing in permanent darkness. Voids in the permafrost that may contain preserved ecosystems from the Ice Age. Ancient animal remains emerging from thawing ground. These are the actual frozen echoes beneath Denali. Not pyramids built by lost civilizations, but natural structures created by geology, climate, and time. And those natural structures have stories to tell. Stories written not in stone tablets or ancient manuscripts, but in ice, in bone, in the slow accumulation of snow transformed into glaciers. To read those stories, we turn now from legend to science, from the imagined to the discovered. From what people claim lies beneath the ice to what researchers have actually found there. In the summer of 2007, a reindeer herder in Siberia was walking along the bank of a river when he noticed something strange protruding from the thawing permafrost. It was the body of a baby mammoth. The calf, later named Luba, was so well preserved that she appeared almost alive. Her trunk was intact, her eyes were closed, her mouth held mud from the moment of her death more than 40,000 years ago. Luba had fallen into a muddy riverbank and been buried quickly. The mud sealed her away from oxygen and scavengers. The permafrost froze her, and the cold preserved her through 400 centuries. She is one of the most complete mammoth specimens ever found, and she is not unique. The permafrost of Alaska and Siberia has yielded dozens of frozen mammoths, along with woolly rhinoceroses, cave lions, ancient horses, steppe bison, and other Ice Age megafauna. These animals are not fossils, not mineralized bones turned to stone. They are actual bodies, frozen tissue, sometimes with hair and skin and internal organs still present. They are time capsules, windows into an Alaska that existed thousands of years ago when the climate was colder, the landscape different, and species that are now extinct walked across tundra and grassland. The preservation is so complete that scientists can extract DNA. In recent years, researchers have sequenced the genomes of woolly mammoths using genetic material from frozen tissue. They have compared mammoth DNA to that of modern elephants, tracing evolutionary relationships and reconstructing how these species diverged. Some scientists have proposed an audacious idea, bringing mammoths back. Using cloning technology or genetic engineering, could we recreate a living mammoth from ancient DNA? Could we take an elephant egg, edit its genome to match that of a mammoth, and produce an animal that has not walked the earth in 10,000 years? The proposal is controversial. Setting aside the technical challenges, which are enormous, there are ethical questions. Is it right to resurrect extinct species? Where would they live? What ecosystem could support them? Would they suffer, confused and alone in a world utterly different from the one their ancestors knew? These questions remain unresolved. But the fact that they can even be asked is a testament to what the frozen ground preserves. Alaska's permafrost is not limited to animal remains. It also contains ancient plants, pollen grains, preserved in lake sediments and frozen soil tell us what vegetation grew during different climate periods. Seeds, sometimes still viable after thousands of years in the freezer, can be germinated in laboratories. In 2012, Russian scientists successfully germinated a narrow-leafed campion plant from seeds that had been frozen in Siberian permafrost for more than 30,000 years. 30,000 years. The seeds were from the Pleistocene, buried by an Arctic ground squirrel in its burrow, frozen before modern humans had spread across most of the world, and they still retain the potential for life. The cold is an extraordinary preservative. In Alaska, researchers drilling into permafrost have recovered pollen assemblages that allow reconstruction of ancient ecosystems. During the last ice age, much of interior Alaska was not covered by glaciers. Instead, it was a cold, dry steppe, dominated by grasses, sedges, and willow shrubs. This was the Mammoth Steppe, a vast grassland ecosystem that stretched from Europe across Siberia and into Alaska. It supported enormous herds of large mammals, mammoths, horses, bison, caribou, and it was very different from the landscape we see today. Modern Alaska, particularly in the interior, is dominated by boreal forest. Spruce, birch, and aspen cover valleys and hillsides. Wetlands and bogs are common. The vegetation is shaped by the current climate, which is warmer and wetter than the Ice Age steppe. But beneath the forest, buried in permafrost, the old ecosystem remains. Bones, pollen, seeds, all frozen in the moment of their deposition, and in some cases, larger structures, ancient forests. During warm periods between glaciations, trees grew in regions that later became too cold or too glaciated to support them. When the climate cooled again, those forests died. In some cases, they were buried by advancing glaciers or covered by sediment and frozen. Now, as glaciers retreat and permafrost thaws, these ancient forests are being exposed. In Glacier Bay National Park, in southeast Alaska, retreating glaciers have revealed stumps and logs from trees that grew more than 1,000 years ago. The wood is still solid, preserved by the cold. Tree rings can still be counted, providing records of ancient climate. Farther north, near the Brooks Range, researchers have found even older wood. Logs from trees that grew during the last interglacial period, more than 100,000 years ago. The wood has been compressed and altered by time and pressure, but it is recognizable, identifiable. Species that still exist in Alaska today, growing in the same region under similar conditions, separated by 100 millennia of ice. The frozen ground holds continuity. It connects the present to the deep past, showing us that the cycles of climate, the advance and retreat of ice, the rise and fall of ecosystems have happened before and will happen again. And it holds one more type of record, perhaps the most important, ice cores. Ice cores are cylinders of ice drilled from glaciers or ice sheets, sometimes extending thousands of feet deep. Each layer of ice represents a year of snowfall, compressed and preserved. Within the ice are tiny bubbles of ancient atmosphere trapped at the moment the snow fell. By analyzing those bubbles, scientists can measure atmospheric composition going back hundreds of thousands of years. They can determine the concentration of carbon dioxide, methane, and other gases. They can identify volcanic eruptions from ash layers. They can reconstruct temperature by analyzing isotopes of hydrogen and oxygen in the ice itself. Ice cores are among the most valuable climate records we have. The longest ice cores come from Antarctica and Greenland, where the ice is thick and ancient. But Alaska's glaciers also provide important records, particularly for understanding climate variability in the North Pacific region. In 2013, researchers drilled an ice core from the summit plateau of Mount Hunter, a peak near Denali. The core extended more than 700 feet deep, representing approximately 1,200 years of snowfall. Analysis revealed detailed records of temperature, precipitation, and atmospheric circulation patterns. The data showed significant climate variability. Warm periods and cold periods, wet years and dry years, all recorded in the layered ice. The medieval warm period appeared in the core, as did the Little Ice Age. Volcanic eruptions from across the Pacific Rim left their signatures in ash and sulfate layers. The mountain had recorded it all. Snowflake by snowflake, year by year, building a frozen archive of climate history. But ice cores do more than record the past. They also help us understand the future. By studying how climate has varied naturally over centuries and millennia, scientists can better understand the changes happening now. The current warming trend can be placed in context. We can see that the rate of temperature increase over the past century is unprecedented in the ice core record. We can see that atmospheric carbon dioxide levels are higher than they have been in at least 800,000 years. The ice tells us that something unusual is happening. And as the climate warms, the ice itself is changing. Glaciers are retreating, permafrost is thawing, the frozen archive is melting, and with it, we are losing records that can never be recovered. Permafrost that took thousands of years to freeze can thaw in decades. Ice caves that have existed for centuries can collapse in a single warm summer. Glaciers that have flowed for millennia can retreat miles in a generation. The frozen echoes beneath Denali are not permanent. They are ephemeral, fragile, at risk, but they are also still revealing secrets. In 2019, a remarkable discovery was made in the Yukon, just across the border from Alaska. Gold miners excavating permafrost found the mummified remains of a wolf pup. The pup was perfectly preserved, with fur, skin, and internal organs intact. Radiocarbon dating showed it had died more than 57,000 years ago. 57,000 years, before modern humans reached North America, before the last glacial maximum, before so much of the history we have discussed in this documentary. And yet here was the pup, looking as if it had died days ago. Its stomach contents were analyzed. The last meal was identifiable: aquatic prey, probably salmon. DNA was extracted and sequenced. The pup was related to both ancient Beringian wolves and modern wolves, helping scientists understand how wolf populations moved and mixed across the Ice Age landscape. Every discovery adds detail to the picture. Every frozen specimen, every ice core, every preserved seed or bone or fragment of wood tells us something about the past, about ecosystems that no longer exist, about climate before human influence, about the long, slow processes that shape landscapes and life. The permafrost and the glaciers are libraries. And we are only beginning to learn how to read them. But reading is not the only challenge. As the ice melts, as permafrost thaws, there are consequences. Carbon stored in frozen soil for thousands of years is released as the ground warms. Methane trapped in ice bubbles up as the ice melts. Ancient bacteria and viruses dormant in the frozen earth may reactivate. The frozen time capsules are opening. Not slowly, carefully, under controlled conditions, but rapidly, chaotically, driven by a warming climate that is reshaping the Arctic faster than anywhere else on Earth. What will emerge? More mammoths, more ancient DNA, more records of past climates, certainly, but also uncertainty. The ecosystems that exist now, the forests and wetlands and tundra, were shaped by the presence of permafrost. As the permafrost disappears, those ecosystems will change in ways we cannot fully predict. The frozen echoes are becoming unfrozen. And the future of Alaska's ice, of the glaciers and permafrost that define so much of the landscape, is uncertain. A dawn breaks over a research camp on the Kahiltna Glacier. Tents cluster in a small depression, sheltered from the wind. Solar panels tilt toward the sun, charging batteries that power laptops and scientific instruments. A weather station records temperature, wind speed, barometric pressure, every data point automatically logged and stored. This is modern glaciology, not the heroic expeditions of the early 20th century, though the work is still difficult and dangerous. Not the solitary prospector stumbling upon caves by accident, but systematic, collaborative science using technology that would have seemed magical a generation ago. Dr. Erin Pettit stands near a drill rig mounted on a metal frame. She is a glaciologist from Oregon State University, and she has spent several seasons working on Alaska's glaciers. Today, her team is drilling through the ice to reach the bedrock below. The drill is a hot water system using pressurized jets of heated water to melt a narrow hole down through hundreds of feet of ice. The work is slow, precise. As the drill descends, sensors are lowered into the hole. Temperature probes measure how heat moves through the ice. Pressure sensors detect meltwater at the glacier's base. Cameras send back images from the darkness below, showing glimpses of the hidden boundary between ice and stone. What they find confirms theoretical models. There is water at the base of the glacier, a thin film just millimeters thick in some places, several centimeters in others. The water is moving, flowing along channels in the bedrock, draining toward the glacier's terminus. The temperature is right at the melting point, held there by the balance between pressure, friction, and cold. This is the engine of glacier movement. The water reduces friction, allowing the ice to slide over bedrock. Without it, the glacier would move much more slowly, deforming internally but not sliding. The hidden hydrology controls the glacier's behavior, its speed, its response to climate. To understand glaciers, you must understand what lies beneath them. This is work that cannot be done from orbit, cannot be measured from a distance. Someone must be there, on the ice, drilling and measuring and collecting data. Other research teams use different methods. Ground-penetrating radar, which we have mentioned before, can be towed behind a snowmobile or a person on skis. As the radar unit moves across the glacier surface, it sends electromagnetic pulses into the ice and records the reflections. Different materials reflect differently. Solid ice produces one signature, water produces another. Air pockets, crevasses, and debris-laden ice each have distinctive patterns. By analyzing thousands of radar traces, scientists can create three-dimensional maps of glacier interiors. In 2016, a team from the University of Alaska Fairbanks conducted a comprehensive radar survey of the Ruth Glacier. They drove snowmobiles back and forth across the ice in a grid pattern, collecting data for days. When the data was processed, it revealed the glacier's hidden topography in unprecedented detail. The bedrock beneath the ice was not smooth, but deeply carved. Valleys and ridges, channels and plateaus, all sculpted by the glacier's movement over thousands of years. In some places, the ice was more than 3,000 feet thick. In others, bedrock rose nearly to the surface, creating hidden obstacles that shaped how the ice flowed around them. The radar also showed something unexpected: bright reflections from the glacier's base, indicating the presence of water. Not just a thin film, but actual pools, pockets of meltwater trapped between ice and bedrock. These subglacial lakes are common in Antarctica, where massive ice sheets press down on bedrock, creating pressure conditions that allow liquid water to exist despite the extreme cold. But they are rarer in Alaska's mountain glaciers. The discovery suggests that the hydrology beneath the Ruth Glacier is more complex than previously thought. Water may be accumulating in bedrock depressions, forming lakes that persist for years or drain suddenly when hydraulic pressure overcomes the ice above. These sudden drainage events, called Yerkel-lorps, can release enormous volumes of water downstream, flooding valleys and reshaping landscapes. Understanding when and where they might occur requires knowing what lies beneath the ice. LiDAR, or light detection and ranging, provides another window into hidden structures. LiDAR works by firing laser pulses from an aircraft and measuring how long they take to return. The technology can measure elevation with extraordinary precision, creating detailed three-dimensional maps of the ground surface. In forested areas, LiDAR can even penetrate through tree canopy, revealing the bare earth beneath. In 2018, the National Park Service conducted a LiDAR survey of Denali National Park. The data revealed features that were invisible on traditional maps. Ancient river channels, now dry, showed where streams had flowed thousands of years ago. Subtle ridges marked the extent of glaciers during previous advances. Sinkholes and depressions indicated where permafrost was thawing, causing the ground to collapse. And in some areas, the LiDAR showed openings, depressions in the ice that might be entrances to caves, collapsed sections where tunnels had given way. These features were flagged for further investigation. Though many are in remote locations, that would require significant effort to reach. LiDAR cannot see beneath solid ice or rock, but it can reveal surface features that hint at what lies below. A depression in a glacier's surface might indicate a void within the ice. A pattern of cracks might suggest that meltwater is flowing underneath, causing the ice above to sag or shift. Interpretation requires expertise, experience, and often ground truthing. Scientists must visit the features identified from aerial surveys, confirming what the data suggests, collecting additional measurements, sometimes discovering that what looked significant from above is mundane up close, or vice versa. Ice drilling provides the most direct evidence. In 2020, researchers from the University of Alaska drilled a core from the summit icefield of Denali itself. Working at more than 18,000 feet elevation, in temperatures that dropped to 30 below zero, they extracted ice cores representing approximately 150 years of accumulation. The elevation made the work extraordinarily difficult. At 18,000 feet, oxygen levels are roughly half what they are at sea level. Every movement requires extra effort. Breathing is labored. The cold is intense, even in summer. Storms can arrive with little warning, trapping teams in tents for days. But the data obtained is invaluable. The ice cores from Denali's summit contain records of snowfall, temperature, atmospheric chemistry, and pollution from sources as far away as Asia. Dust from industrial activity in China has been detected in the ice. Radioactive isotopes from nuclear weapons testing in the 1950s and 60s appear as distinct layers. The mountain records global events. It sits in the middle of atmospheric circulation patterns that transport air across the Pacific. Everything that happens upwind eventually leaves a trace in Denali's ice. All of this research, the drilling and the radar and the LiDAR, is building toward a comprehensive understanding of Alaska's frozen systems, how glaciers form and flow, how permafrost develops and degrades, how climate shapes the landscape over decades, centuries, millennia, how water moves through frozen environments, carving caves and channels that exist briefly or persist for generations. The work is ongoing. Every field season brings new data. Every publication adds to the collective knowledge. Slowly, the hidden world beneath Alaska's ice is being mapped, measured, understood. But there are limits. Denali National Park alone covers more than 6 million acres. Much of it is wilderness, accessible only on foot or by small aircraft. Glaciers are dangerous, constantly changing. Permafrost is difficult to study without disturbing it. And funding for research, always limited, cannot support comprehensive exploration of every glacier, every frozen valley, every potential ice cave. So priorities are set. Scientists focus on glaciers that are changing rapidly, that provide the best climate records, that are accessible enough to study safely. They use remote sensing to identify areas of interest, then ground truth the most promising sites, and they collaborate with each other across institutions and countries, with the National Park Service, which manages access to protected areas and supports research that enhances understanding of park resources, with Indigenous communities, whose traditional knowledge often identifies features and patterns that scientific methods alone might miss. One such collaboration occurred in 2017. Researchers working near the Kantishna Hills on the northern edge of Denali National Park were trying to understand permafrost distribution in the region. They were using standard techniques, drilling boreholes, measuring ground temperatures, mapping vegetation patterns. A local Athabascan elder asked to see their maps. He pointed to several areas where the researchers had assumed permafrost would be continuous. He told them that in those locations, the ground had always been soft, even in winter, that hunters knew not to cache meat there because it would not freeze reliably. The researchers adjusted their survey, and the elder was correct. In the areas he had identified, permafrost was absent or discontinuous, despite being present in adjacent areas with similar aspect and elevation. Subtle variations in hydrology, in snow accumulation, in vegetation, created localized warm spots that scientific models had not predicted. Traditional knowledge had identified what the technology missed. This kind of collaboration is becoming more common and more valued. Science benefits from the deep, multi-generational understanding that indigenous peoples have of their lands, and indigenous communities benefit when research supports their efforts to protect traditional areas and understand how climate change is affecting the resources they depend on. The frozen world beneath Denali is not just a scientific problem to be solved. It is a living landscape, a cultural heritage, a repository of deep time, and an ecosystem responding to rapid change. Understanding it requires multiple ways of knowing: field measurements and oral history, radar surveys and stories, ice cores and traditional place names. All of these sources contribute to a richer, more complete picture of what lies beneath the ice, and all of them point to the same conclusion: there is more to discover. There are glaciers in the Alaska Range that have never been explored. Glaciers without names, appearing on maps as white spaces between peaks, their termini buried in remote valleys where no trails lead. Some are small, remnant ice patches clinging to north-facing slopes. Others are substantial, miles long, thick enough to carve bedrock, old enough to contain ice from centuries past. No scientist has drilled them. No radar has mapped their depths. No one knows what caves or channels might exist within them. They remain hidden in plain sight. This is one category of mystery that still surrounds Denali and the Alaska Range. Not ancient pyramids or lost civilizations, but straightforward geographical unknowns. Places that are simply too remote, too difficult to access, too dangerous to explore with current resources and technology. How many ice caves exist in these unexplored glaciers? We do not know. We can estimate, based on what we have found in the glaciers we have studied. We can model cave formation using our understanding of glacial hydrology, but we cannot know for certain without going there, entering the ice, mapping what we find. And new caves are forming constantly. Each summer, as temperatures rise, meltwater carves new channels through glacial ice. Some of these channels are small, ephemeral, freezing shut in winter. Others grow larger year after year until they become true caves, accessible passages extending deep into the glacier. Each winter, some caves collapse. The glacier moves, stresses build, and the roof gives way. What was open becomes closed. What was accessible becomes buried. The ice erases its own structures and creates new ones. Mapping this dynamic system completely is impossible, but that does not mean we cannot learn more. Technology continues to improve. Drones equipped with thermal cameras can identify areas of ice melt that might indicate caves beneath the surface. Autonomous underwater vehicles, small enough to deploy in subglacial streams, could explore drainage systems that humans cannot reach. Satellite radar, using interferometry, can detect subtle changes in glacier surface elevation. If a large cave collapses, or if a subglacial lake drains, the ice above sinks. Satellite instruments can measure this subsidence, sometimes to within millimeters. By monitoring glaciers over time, scientists can identify dynamic areas where hidden processes are reshaping the ice. These technologies are expanding what we can know about the frozen underground, but they also raise new questions. In 2021, satellite monitoring detected a sudden subsidence event on a glacier in the Alaska Range. Over the course of just a few days, an area roughly the size of a football field dropped nearly 10 feet. Something beneath the ice had changed. A cave had collapsed, or a pocket of meltwater had drained, or perhaps a section of the glacier had detached from bedrock and settled. Researchers noted the event, marked the location, and added it to a list of sites for potential future investigation. But no one has visited the site. It is too remote, accessible only by helicopter in good weather, and the glacier itself is crevassed and unstable. Going there would be risky, expensive, and might not yield significant findings beyond confirming what the satellite data already suggests. So it remains a mystery. A small one, specific and localized, but real. Multiply that by hundreds of glaciers, thousands of square miles of ice, and you begin to appreciate the scale of what remains unknown. Permafrost presents similar challenges. We know that voids exist within frozen ground. We have detected them with ground-penetrating radar. But we rarely excavate them, rarely see them directly. What percentage of Alaska's permafrost contains significant voids? We do not know. The percentage is probably small, but even a small percentage of millions of square miles is a substantial area. And as permafrost thaws, new discoveries are being made. In 2019, a hiker in Denali National Park reported finding a depression in the ground that had not been there the previous year. Park rangers investigated and found that a section of permafrost had thawed and collapsed, creating a sinkhole roughly 15 feet across and 8 feet deep. At the bottom of the sinkhole was a tusk, a mammoth tusk, eroding out of frozen sediment. The rangers contacted paleontologists from the University of Alaska who excavated the site carefully. They recovered not just the tusk, but several other bones, including a partial skull and sections of vertebrae. The mammoth had died approximately 30,000 years ago, and for 30,000 years it had been frozen, preserved, waiting, until a warming climate thawed the permafrost and the ground collapsed, and a hiker happened to walk by at the right moment. How many other mammoth remains are still frozen, still waiting? How many archaeological sites, evidence of the first peoples who lived in Alaska, lie buried beneath permafrost? In coastal erosion zones, where rivers and ocean waves are cutting into frozen bluffs, artifacts are emerging. Stone tools, hearths, bone fragments, all appearing in the thawed sediment. Archaeologists work quickly when sites are found, racing against further erosion that will destroy what the ice preserved. In 2015, a site near the village of Kaktovik, on Alaska's Arctic coast, yielded tools dated to more than 12,000 years ago. The tools were sophisticated, showing continuity with other Paleo-Indian traditions across Beringia. But the site was eroding rapidly, undermined by thawing permafrost. Within a few years, much of it had collapsed into the sea. What was lost, we will never know, perhaps only a small hunting camp briefly occupied. Or perhaps something more significant, a seasonal settlement, a cache of tools and supplies, evidence of how people lived in the Ice Age Arctic. The frozen ground held the answers, and then the frozen ground thawed, and the answers vanished before we could read them. This is the urgency that now surrounds Alaska's ice. It is melting, thawing, retreating, and as it disappears, it takes with it records that cannot be replaced. Ice cores that extend back thousands of years, representing climate history that exists nowhere else. Frozen specimens of extinct animals with tissue and DNA intact. Archaeological sites sealed in permafrost, preserving organic materials that would have decayed anywhere else. All of it is vulnerable. Climate models project that Alaska will continue to warm faster than the global average. Glaciers will continue to retreat. Permafrost will continue to thaw. The frozen world that has defined the region for millennia is entering a period of rapid transformation, and we are witnessing it. Scientists working in Alaska today are documenting changes that their predecessors only decades ago could not have imagined. Glaciers that once terminated on land now end in lakes. Ice caves that were stable for years collapse in single seasons. Rivers that flowed beneath glaciers now flow on the surface as the ice thins and retreats. The hidden is becoming visible, but not in a controlled, systematic way. Not through careful excavation and documentation, through melting, collapsing, eroding, through processes we can observe but not stop. What will remain hidden? Some caves, deep within the most stable glaciers, may persist for decades or centuries more. Some permafrost, in the coldest regions, at the greatest depths, will remain frozen even as surface layers thaw. Some secrets will stay buried, but many will not. And the question facing researchers is how to document and understand what is being revealed, how to prioritize limited resources, how to save what can be saved of the frozen archive before it is gone. There are no easy answers. Only the certainty that the frozen echoes beneath Denali, beneath all of Alaska, are changing. What was permanent is proving temporary. What was hidden is being exposed. What was known is becoming unknown again as the ice that preserved it disappears. The mountain endures. The stone remains. But the ice, the frozen layers that have shaped the landscape and preserved its history, is melting. And with it, a particular kind of Alaska is passing away. Not the Alaska of myths and legends, of buried pyramids and ancient aliens, but the Alaska of deep cold and permanent ice. Of glaciers that seemed eternal, of permafrost that was always frozen. That Alaska is becoming a memory, recorded in photographs and data sets, in ice cores stored in freezers, in the journals of explorers and the observations of indigenous elders. Remembered, but no longer present in the same way. What comes next is uncertain, but the questions remain. And as long as ice exists in Alaska, as long as glaciers flow and permafrost grips the ground, there will be mysteries beneath the surface. Caves to discover, channels to map, records to read. The work continues. Quietly, persistently, in field camps and laboratories, in conversations between scientists and elders, in the slow accumulation of knowledge that defines all real exploration. Not the dramatic revelations of fiction, but the patient work of understanding. The frozen world still has much to teach us if we listen carefully. If we look closely, if we respect what we find and preserve what we can, the mountain watches over it all, silent, enduring, waiting. Night settles over Denali. The sun descends slowly, taking hours to sink below the horizon. The light fades through shades of gold and amber, rose and violet, deepening gradually into twilight. In midsummer, this far north, true darkness never comes. The sky remains luminous, a deep blue glow along the northern horizon where the sun rolls just beneath the edge of the world. But in autumn, darkness returns. Stars appear one by one, then in multitudes. The Milky Way arches overhead, so bright it casts shadows on the snow. Constellations wheel slowly through the night, marking the passage of hours with ancient, patient movements. The mountain rises into the starlight. A presence darker than the sky, a void in the field of stars, defined by its own immensity. No lights mark its slopes. No fires burn on its flanks. It is simply there, as it has been for millions of years, as it will be for millions more. Silent. The wind has stilled. After days of storm, of blowing snow and bitter cold, the air has gone calm. The kind of calm that feels almost tangible, a presence in itself. In this stillness, you can hear the mountain. The creak of ice shifting within a glacier, a sound so low it is felt more than heard, a vibration transmitted through stone and snow. The crack of a crevasse opening somewhere high on the peak, sharp and sudden, echoing off the surrounding ridges. The whisper of spindrift sliding across a windswept ridge. These are the sounds of deep time, of processes too slow for human perception, made audible only in moments of perfect quiet. The mountain breathing, the ice moving. The stones settling under the weight of snow and gravity, and the slow, inevitable pull of the earth. Below the mountain, in the valleys, other sounds emerge. A stream flowing beneath a bridge of snow, its water hidden but audible, a gentle murmur in the darkness. The distant howl of a wolf, calling to others of its pack, the sound carrying for miles across frozen tundra. The soft hoot of an owl, hunting in the spruce forest that borders the park road. Life persists, even here, even now, in the cold and the dark. Adapted, resilient, at home in conditions that would be lethal to those not prepared for them. Snow begins to fall, not a storm, just a gentle descent of flakes, drifting down through the still air, accumulating on surfaces with the softest of sounds, a whisper, a hiss. The quiet accumulation of winter. Each snowflake is unique, a crystalline structure formed in the upper atmosphere, shaped by temperature and humidity, falling through miles of sky to land here, on this particular slope, at this particular moment. And here it will remain, unless wind moves it, unless sun melts it. It will be buried by other snowflakes, compressed under their weight, transformed slowly into firn and then into ice. In 1,000 years, if it has landed on a glacier, it might flow down the mountain, a tiny component of the vast river of ice, carrying within it bubbles of atmosphere from this night, this moment, a record, a memory, a frozen echo. The stars continue their slow rotation. Polaris holds steady in the north. Cassiopeia tilts through her slow arc. Orion rises in the east, the hunter climbing into the winter sky, his belt bright, his sword hanging below. The same stars the first peoples saw when they traveled through these lands. The same stars the explorers navigated by. The same stars that will shine long after we are gone, unchanging in human time, changing profoundly in the deep time of the cosmos. The glaciers know this. They move according to rhythms older than human history. They respond to climate shifts that play out over centuries. They care nothing for our urgency, our need to understand and explain and categorize. They simply exist, flowing, carving, preserving. Beneath them, the hidden rivers continue their dark journey. Water flowing where no light reaches, carving channels, dissolving stone, moving steadily toward the distant sea. Beneath the permafrost, the frozen ground holds its treasures, bones and seeds and memories of ecosystems that no longer exist, all waiting, preserved, patient. The mountain dreams of ice. Of the great glaciations, when ice covered the world, when the Alaska Range was buried except for the highest peaks, islands in a frozen ocean. It dreams of warmth, of interglacial periods when forests grew higher on its slopes than they do now, when the glaciers retreated to the highest cirques. It has seen all of this before, the advance and retreat, the freezing and thawing, the endless cycle, and it will see it again. Whatever changes come, whatever the climate does, the mountain endures. Stone is patient. Stone remembers, not in the way ice remembers, preserving specific moments, but in its structure, its layers, the slow record of uplift and erosion written in granite and schist. The mountain is a text, if you know how to read it. But tonight, reading is not required. Understanding is not necessary. Tonight, it is enough to simply be here, in the presence of something vast and old and indifferent to human concerns. Something that existed long before we arrived and will exist long after we are gone. There is comfort in that, in knowing that not everything depends on us, that there are processes and cycles and rhythms that will continue regardless of what we do or fail to do. The mountain does not need us to climb it, to name it, to study it. It simply is. The snow continues to fall, silent and steady, covering tracks, smoothing contours, erasing the small marks of human passage. By morning, the landscape will look untouched, pristine, as if no one has ever been here. And in the vast majority of this place, that is true. Most of the Alaska Range has never felt a human footprint. Most of its glaciers have never been entered. Most of its frozen valleys have never been crossed. It remains wild, unknown, free, and beneath it all, in the darkness under the ice, in the sealed chambers of permafrost, in the hidden rivers and unmapped caves, the frozen echoes wait, echoes of the past, of ice ages and interglacials, of mammoths and the first peoples, of explorers and scientists and all who have sought to understand this place, echoes of the present, of ongoing change, of melting and thawing and transformation, and echoes of the future, of what might be found, of what might be lost, of what will endure. The mountain holds them all, in silence, in cold, in the slow, patient accumulation of snow transforming into ice, year by year, century by century, millennium by millennium, your breathing slows. The cold is no longer uncomfortable. You have been still long enough that your body has adapted, found equilibrium with the environment. The down parka traps warmth. The insulated boots keep your feet from freezing. You could stay here, watching the snow fall, watching the stars wheel overhead. Time seems to slow. Or perhaps you are simply slipping into the rhythm of this place, where urgency has no meaning, where change is measured in geological time. The quiet deepens. Even the small sounds, the settling snow, the distant stream seem to fade. Or perhaps you are simply accepting them, no longer distinguishing between sound and silence, between yourself and the vast frozen world around you. Denali rises above you, a darker darkness against the night sky. The Great One, the High One. The mountain that has been called by many names but remains, fundamentally, itself, unchanged by names, undiminished by attempts to claim it or understand it or conquer it, simply present, simply here. And you are here with it, in this moment, in this place, where the frozen echoes gather and wait and whisper their old, patient stories. The snow falls, the stars turn, the mountain sleeps. And you, wrapped in warmth, surrounded by cold, held by the immensity of stone and ice and silence, begin to drift, not into dreams exactly, into something deeper and quieter than dreams, into the stillness that exists beneath thought. The peace that comes from surrendering the need to understand, the need to explain, the need to know, accepting mystery, accepting vastness, accepting that some questions have no answers and that this is as it should be. The frozen world holds you gently. The darkness is not frightening but comforting. The cold is not hostile but neutral, a simple fact, like gravity or time. You are small beneath the mountain, smaller than the ice, smaller than the stone, smaller than the long, slow processes that shape landscapes and climates and the passage of millennia. And that smallness is a gift. It frees you from the burden of significance, from the weight of trying to matter, to make a mark, to be remembered. Here, beneath Denali, you do not matter, and it is a profound relief. You can rest. The mountain will keep watch. The ice will continue its slow journey. The stars will turn through their ancient patterns. Nothing is required of you, only to be here, to witness, to allow the frozen silence to settle around you like snow, soft and encompassing. Your eyes close. The last thing you see is the faint glow of starlight on snow. A luminescence that seems to come from within the ice itself, as if the glaciers hold their own light, gathered over centuries from 1,000 nights like this one. Beautiful, peaceful, still. And in that stillness, in that vast, frozen quiet beneath the mountain, you find what you were seeking all along. Not answers, not explanations, not solutions to mysteries or revelations of hidden things, but simply this, rest, deep, genuine, untroubled rest. The kind that comes only in places where time moves differently, where the concerns of the everyday world fall away, made insignificant by the presence of something so much larger. The mountain endures, the ice preserves, the frozen echoes wait. And you, small and quiet and finally at peace, sleep beneath the stars, beneath the mountain, beneath the eternal, patient, silent ice. Thank you for joining this journey into the frozen silence beneath Denali. May your rest be as peaceful as the quiet valleys, as deep as the ancient ice, and as enduring as the mountain itself. If you found peace in this exploration of history and ice, consider sharing it with others who seek calm in the stories of the past. Sleep well.